because this quantity is known. Now, why is it interesting to design this kind of structure? We call this a filter, and why does it work? Because if you go and compute the evolution of the difference, let me call this estimation error. You see what this quantity is? This is the difference between the real state and the estimated state. Okay? Now, if you compute the dynamics of this quantity, it turns out, given the filter structure, that the dynamics of this quantity is exactly this. X tilde dot is equal A by construction. Now what Kalman and the other researchers working on state space approaches have proven is that if the matrix, if the couple AC is observable, okay, if it is observable, then you can always choose a matrix K such that the eigenvalues of this matrix, A plus KC, are assigned at will. Okay? And that's extremely important because you should know, and you probably remember, that the eigenvalues of this matrix are telling you how the evolution of the state of X tilde. If those are all in the left complex plane, all the components of X tilde will go to 0 exponentially. Okay? So this will mean that X hat will converge on X, because X tilde will converge on 0. Okay? So if the pair AC is observable, I can always find a matrix K such that the eigenvalues of this matrix are in the left-hand side plane, and this filter will have an evolution, no matter how I initialize it, such that X hat exponentially converges to the real X. And that's how you solve the trick. Okay? Then there are numerical methods to actually do what I told you here. I mean, suppose I want to assign the eigenvalue of this matrix. I know A, I know C, and my unknown is K. There are numerical methods. MATLAB or any other software similar to MATLAB have these routines already implemented, where you give a pair AC that is observable, you tell the software where you want the eigenvalues, and you get K out for free as a result. And then how do you use this K matrix? You put it in here. That's how you use K matrix. This is your filter. This is your observer. This is called Luenberger observer, by the name of the person who first suggested it. Actually, observer is made of these two equations. You have the state estimation equation and the output equation. Okay, this is what I just said, so nothing more. Okay, in the stochastic case, now let me come back here. You see, in all what we said today, we never talked about noise. So we took a deterministic state equation and a deterministic output equation. If you add noise, things become a little bit more complex, but I mean the basic results and the basic ideas are the same. So what happens is that if you do add noise, the Luenberger observer will also produce a state estimator that is affected by noise, of course, because you will inject noise by here. If Y is a measurement that includes noise, I will get noise in my state estimate because I have noise here, right? Okay. So just let me give you the basic ideas. No maths, no details. The basic idea of the Kalman filter. Well, why is the Kalman filter so popular and so well known? And what is it actually doing? Well, what the Kalman filter is doing is the following. If you do get noise in the state estimation because of the signal Y you have here, you can also, and if you assume that this noise is zero mean and Gaussian, okay? Those are the working hypotheses of the Kalman filter. You can prove that the noise on the state estimate will be again Gaussian. Okay? And the covariance of this noise, the covariance on the state estimate, will depend on what? Well, it will depend, of course, on the covariance of the noise that you're injecting through the measurement, and it will depend also on the size of and on the structure of this matrix K. The covariance of the state estimate will depend on that K matrix. Okay? So the whole story about the Kalman filter is this. Choose the K matrix such that the covariance on the state estimate is minimized. So to have the optimal state estimate in the sense that it's the one with the least covariance, with having a noise that has the least covariance. Okay? If you go through the maths of this, then you recover the well-known Kalman filter. So Kalman filter is nothing else than a Leuenberger filter. It has exactly the same precise structure, but the K matrix is not chosen, let's say, randomly, or, well, Leuenberger does not choose it randomly, it just chooses it such that the eigenvalues of these things are stable, are in the left complex plane. What the Kalman filter is doing is a bit more. Not only it guarantees that the filter is stable, so that the eigenvalues of these will be in the left-hand side plane, but it also guarantees, by construction, that the covariance of the state estimate, the covariance of the state estimate will be minimized. That's what the Kalman filter is doing for linear systems. Okay, yeah, this is just a verbal description of the stochastic case. Okay, so that was it for the preliminaries, so to say, although it took kind of long. And now I wanted to show you some results